Right now, without your permission, you're moving at roughly 2,000 kilometers an hour. Not metaphorically, not eventually. Right now, in the chair, on the floor, wherever you happen to be sitting still, absolutely certain that nothing is happening. Nobody warns you about this one. There's no moment in school where someone sits you down and says, "By the way, you have never once in your life been stationary, not for a second, not even in your sleep, and you never will be, because there is nowhere in the universe still enough to rest against. Somewhere in your own memory there's probably a night you lay on your back outside looking up, feeling completely still, feeling like the ground under you was the one motionless thing in an otherwise moving universe. It wasn't, it never was, and once you know that, you don't really get to unknow it. Let's start with the part that's almost embarrassing once you actually do the arithmetic. The Earth spins. Everyone knows the Earth spins. But knowing it and feeling the number are two different things, and the number, for most people standing near the equator, works out to something like 1,600 kilometers an hour, just from the planet turning underneath you once a day. You're not walking that fast. You're not driving that fast. You're being carried that fast continuously by the simple rotation of the ground you've mistaken your entire life for the one fixed thing. That's the smallest of the motions. It's the one closest to home, the one built into every sunrise and sunset you've ever watched. The visible proof of a spin most people never actually connect to their own body moving through space at highway plus speeds without a single sensation of it. Then there's the bigger motion sitting underneath that one, patient, indifferent, the one carrying the entire spinning Earth along with it. The whole planet, spin included, is also orbiting the Sun, tracing an enormous loop that takes an entire year to complete, moving at something close to 107,000 kilometers an hour to make that loop happen on schedule. Add that number to the spin, and depending on where you happen to be standing when you do the math, you're being carried through space at speeds that would sound, if applied to literally anything else you could picture, either impossible or terrifying. None of it feels like anything. That's the part worth sitting with before going any further. Speed, on its own, was never something a body could feel directly. What a body feels is change, is acceleration, is the jolt of a car braking or a plane hitting turbulence. A steady speed, however enormous, simply disappears into the background, indistinguishable from standing perfectly still, because in every sense your body actually has access to. Standing still and moving at 100,000 kilometers an hour are exactly, precisely, the same experience. There's a slightly more technical wrinkle buried in the spinning part specifically, one worth mentioning honestly rather than glossing over. Spinning motion does technically involve a small continuous acceleration, a gentle inward pull needed to keep anything on a curved path rather than flying off in a straight line. The same basic effect that presses you sideways gently in a car taking a slow, wide turn. For the Earth's rotation, that inward pull works out to something tiny, roughly 0.03% of ordinary gravity, easily lost entirely within the much larger, much more noticeable pull of gravity itself holding you to the ground. It's there. It's real. It's simply far too small compared to gravity for any human sense to separate it out and notice it as anything distinct. To put the actual numbers into some kind of perspective, consider the fastest object humanity has ever built. A spacecraft launched specifically to study the Sun up close, using repeated gravitational assist from Venus to gradually tighten its orbit, has been clocked passing the Sun at speeds exceeding 600,000 kilometers an hour, the fastest anything made by human hands has ever traveled. That number sounds, and is extraordinary, a genuine engineering achievement worth marvelling at on its own terms, and yet it's only a few times faster than the Sun's own ordinary orbital speed around the galaxy's centre, a speed the entire solar system, including you, has simply always had, for free, without any engine, without any launch, without anyone ever having to build anything at all to achieve it. That comparison is worth sitting with for a moment, because it inverts something people tend to assume without ever quite examining it. The fastest thing humanity has ever engineered, the product of decades of careful design and enormous expense, still falls short of matching the ordinary background speed every single person has always been travelling at, simply by virtue of living on a planet that happens to orbit a star that happens to orbit a galaxy. Extraordinary engineering, measured against ordinary cosmic motion, turns out to be a fairly modest achievement. There's a particular kind of humility available in that comparison, one that doesn't require any dramatic reframing to access. Every rocket ever launched, every engineering triumph ever celebrated for reaching some new record speed, has been chasing a number the universe handed out for free, built into the basic architecture of any planet orbiting any star inside any galaxy. The achievement of engineering isn't matching that background speed. It's doing anything useful with the comparatively tiny additional push a rocket engine can actually provide, layered on top of a foundation of motion that was never actually built by anyone. I think that's the sentence that should probably unsettle you most out of everything said so far, more than any of the specific numbers. Your body has no instrument capable of detecting the difference between rest and motion, not when the motion is smooth, not when nothing is pushing back against it. Every certainty you've ever had about being still was never actually a measurement. It was an absence of evidence, mistaken for proof. This isn't just a quirk of human perception either. It's a genuine foundational feature of how physics itself works, one that took centuries of careful argument to fully accept. There is no experiment you could run, sealed inside a windowless room moving at a perfectly steady speed, that would ever tell you whether that room was at rest or in motion. Drop a ball, and it falls the same way either way. Bounce it, and it bounces the same way either way. The laws of physics simply don't care about steady motion, don't distinguish between a room parked on the ground and a room hurtling through space at any constant speed you care to name, so long as nothing is accelerating, nothing is changing direction, nothing is pushing back. Stillness, in the deepest sense physics can define it, was never a real category to begin with. Only sameness of motion, relative to something else, ever really existed. That single realization, once it was fully worked out, quietly undid a picture of the universe that had felt obviously true for almost the entirety of human history. For most of that history, the ground beneath anyone's feet was assumed, reasonably enough given the available evidence, to be the one fixed, unmoving centre around which everything else, sun included, was doing the actual travelling. It took centuries of resistance, argument, and eventually overwhelming evidence to establish the opposite arrangement, that the ground itself was the thing doing the moving, spinning and orbiting both, and that the feeling of fixed stillness underfoot had been, this entire time, nothing more than the natural consequence of moving too smoothly to notice. There's a deeper layer to this same idea worth including, honestly, even though it complicates the picture slightly. Gravity itself, the thing holding you to the ground and making that ground feel like a fixed, stable reference point, is intimately tied up with acceleration in ways that took even longer to fully work out than the basic fact of the Earth's motion. An object in true free fall, falling without any air resistance, experiences something remarkably close to weightlessness. The same sensation astronauts feel orbiting the planet, not because gravity is switched off, but because falling and orbiting are, in a very real physical sense, the same kind of motion, a continuous state of falling that simply never reaches the ground because the Earth's surface curves away underneath at the same rate the object falls toward it. Standing on solid ground, feeling gravity pull you downward, and feeling the ground push back up against your feet is actually a kind of interrupted fall, a fall that gets stopped continuously, moment to moment, by the solid material underneath you refusing to get out of the way. Remove that ground, and you'd simply keep falling, the same way the space station keeps falling around the Earth indefinitely, orbit after orbit, without ever actually landing. And this is still, somehow, only the beginning of how fast you're actually going. Because the sun itself, carrying the Earth, carrying you, carrying everyone you've ever met, isn't sitting still either. It's caught in its own far larger loop, one that makes the yearly trip around it look almost trivial by comparison. That loop is the one this whole exploration is really about, the one most people go their entire lives without ever being told exists, and once you've heard it, sitting still, ever again, doesn't quite mean what it used to. Before going further, if any of this is landing the way it's meant to, land somewhere that keeps sending it. The kind of following where it just shows up again on its own is the only ask being made here, and even that's said reluctantly, because the sitting with the idea itself matters more than any button anywhere ever could. Here is the bigger loop. The sun, along with everything orbiting it, is itself in orbit, around the centre of the galaxy it belongs to, a slow, enormous circuit that takes roughly 220 million years to complete just once. Not once a day, not once a year, once every 220 million years, a span of time so long that the last time the solar system was in its current position relative to the galaxy's centre, there were no flowering plants anywhere on Earth, no birds, nothing resembling most of what would eventually become familiar life, and dinosaurs, when they eventually showed up, would live and go fully extinct before the loop finished even a single full turn. To make that orbit happen at all, the sun has to be moving at a speed that makes the earlier numbers look almost quaint, roughly 230 kilometers a second, not an hour, a second. Multiply that out and the sun, carrying its entire collection of planets, moons, asteroids, and one particular species currently reading about it, is covering something like 800,000 kilometers every single hour, sweeping through the galaxy on a track so wide that no human measurement of time has ever come close to capturing a meaningful fraction of the full loop. Sit with that scale difference for a moment, because it matters. The spin of the Earth, a day. The orbit around the sun, a year. The orbit around the galaxy, 220 million years. Each layer of motion operates on a timescale so much longer than the one before it that comparing them starts to feel almost dishonest. The way comparing a heartbeat to a heartbeat isn't quite fair when one of them belongs to a mayfly and the other belongs to a mountain range slowly eroding. It took a surprisingly long time in the history of astronomy for anyone to even establish that the sun was orbiting anything at all, let alone work out the size and duration of the loop. For most of recorded history, the sun's position relative to the rest of the galaxy simply wasn't a question anyone had the tools to ask, because nobody yet understood that the fuzzy band of light stretched across a dark night sky the one now called the Milky Way, was actually the edge-on view of a disc-shaped structure containing billions of other stars, with our own sun embedded somewhere inside it, rather than sitting at the centre of everything. Once that picture came into focus, in the early 20th century, the natural next question, obvious in hindsight but genuinely difficult at the time, became whether the sun was simply sitting still within that disk or moving along with it. The answer, once astronomers had the tools to measure the motions of enough surrounding stars carefully enough, turned out to be motion, substantial motion, in a roughly circular path around a distant invisible centre. Long before anyone had confirmed the sun's orbit around the galaxy, though, a much simpler and more direct demonstration had already settled the more basic question of whether the Earth itself was actually spinning, a question that had generated centuries of philosophical and religious resistance before finally being settled by an experiment almost embarrassingly simple in its construction. In the middle of the 19th century, a physicist suspended a heavy weight from a long wire beneath the dome of a building in Paris, setting it swinging gently back and forth in a single, fixed plane. Over the course of several hours, without anyone touching it, the plane in which the pendulum swung appeared to slowly rotate, tracing out a full circle over roughly a day. The pendulum itself wasn't actually turning. It was doing exactly what a pendulum does, swinging back and forth along the same fixed plane the whole time. What was turning was the building, the city, the entire ground beneath the dome, rotating slowly underneath a pendulum that had no reason to rotate along with it. For the first time, the Earth's spin had been demonstrated directly, indoors, without needing to look at a single star, simply by hanging a weight from a wire and letting it swing. Confirming the Sun's much larger orbit around the galaxy required an entirely different technique, one that had to wait for instruments capable of measuring extremely small shifts in the light of distant stars. By carefully tracking how the light from stars in different directions was shifted, some very slightly toward the blue end of the spectrum, others very slightly toward the red, astronomers were able to piece together a coherent picture of rotation, stars on one side of the sky consistently approaching, stars on the opposite side consistently receding, exactly the pattern you'd expect if the entire system, sun included, were circling some distant common centre. The technique is a direct ancestor of the same basic method that would later reveal the cosmic microwave background's dipole, and later still the pull of the Great Attractor itself, each discovery building on a version of the same underlying trick. Watch how light shifts, and let that shift tell you about motion nothing else could have revealed directly. That centre itself turned out to be occupied by something worth pausing on briefly, even though it isn't the main subject of this particular exploration. At the heart of the galaxy's orbit sits a supermassive black hole, millions of times the mass of the Sun, anchoring the orbits of everything in the surrounding disk the way the Sun anchors the orbits of the planets, just at a scale so much larger that the Sun itself, along with everything orbiting it, amounts to little more than a single grain of sand circling at a respectful distance from something far heavier sitting in the true centre. Here's a detail that tends to surprise people more than the raw speed itself. The stars making up the familiar constellations, the ones that have looked essentially unchanged across every human lifetime on record, aren't actually fixed relative to each other at all. Each one is orbiting the galactic centre on its own slightly different path, at its own slightly different speed, some faster, some slower, some tilted at a slightly different angle than the Sun's own orbit. Over spans of tens of thousands of years, spans still absurdly short compared to a single full galactic orbit, these small differences accumulate into genuinely noticeable shifts. The familiar shape of a constellation seen tonight is not the same shape it held 10,000 years ago, and it will not hold the same shape 10,000 years from now. Astronomers can calculate with reasonable confidence what the night sky will look like 50,000 years into the future, and the honest answer is recognizably different. Several of the most familiar patterns stretched, skewed, or broken apart entirely. Not because anything catastrophic happened to any of the stars involved, but simply because each one has quietly continued along its own slightly different orbital path this whole time. The way pieces on separate conveyor belts drift apart even when they start out looking neatly aligned. There's a formal concept astronomers use to describe the Sun's motion relative to this whole shifting neighbourhood, called the local standard of rest, essentially an average of the motion of stars in the Sun's general vicinity, used as a convenient reference point since there's no single genuinely fixed marker anywhere nearby to measure against directly. Even that average turns out to be an approximation built out of necessity rather than any real, stable anchor. The Sun actually moves slightly faster than this local average, drifting gently relative even to its own immediate stellar neighbourhood, a small motion layered on top of the larger orbit, itself layered on top of the Earth's motion around the Sun, itself layered on top of the Earth's daily spin. Every layer, once you look closely enough, turns out to be relative to some other layer, and none of them, all the way down, ever quite reaches a layer that could honestly be called still. It's worth asking, briefly, why any of this feels so hard to hold on to, why a fact this well established, this thoroughly measured, still manages to feel almost unreal every time it's stated plainly. Part of the answer has nothing to do with astronomy at all, and everything to do with the kind of senses evolution happened to build. Human perception developed to track threats and opportunities at walking pace, running pace, at most the pace of a thrown spear or a falling branch. Nothing in that evolutionary history ever needed to register speeds measured in hundreds of kilometers per second, because nothing dangerous, nothing useful, nothing relevant to survival ever moved at anything close to that scale. The senses that kept early humans alive were never built to notice galactic motion, and they never needed to be, which is exactly why none of this shows up anywhere in ordinary experience, no matter how real, how measured, how thoroughly confirmed the underlying numbers turn out to be. It helps, a little, to line these speeds up next to each other, because the jump between each one is where the actual strangeness lives. Astronauts aboard the space station orbiting overhead right now are moving at around 28,000 kilometers an hour, fast enough to circle the entire planet roughly every 90 minutes, a speed already well beyond anything a human body could survive colliding with directly, and yet it amounts to barely more than a rounding error compared to the Earth's own orbital speed around the Sun. The Moon, meanwhile, drifts away from Earth at a rate of about 4 centimeters a year, a motion so slow it barely counts as motion at all on any human timescale, and yet even that glacial drift is a real, measured, ongoing departure, the Earth and Moon slowly loosening their grip on each other by roughly the thickness of a fingernail every 12 months. Set that number beside the Sun's 230 kilometers a second sprint around the Galaxy's centre, and the range of speeds involved in this one solar system alone stretches from barely perceptible to genuinely staggering. All of it happening simultaneously, all of it equally real. none of it registering as anything to the person standing on the ground trying to feel any of it directly. And even this, the spin, the yearly orbit, the 220 million year galactic circuit, still isn't the full account of how much motion you're actually caught up in without ever noticing a single bit of it. Because the galaxy itself, the whole enormous spinning disk of it, containing the Sun and its slow orbit and the Earth and its faster one and you sitting there, convinced of your own stillness, is also moving, not spinning in place, moving, going somewhere. And the story of figuring out where and how fast and why turns out to be one of the stranger detective stories in modern astronomy, one that started the way a lot of strange discoveries do, as an error nobody could quite explain away. It's worth pausing before moving into that story properly to notice something about the shape of what's already been covered. Each layer of motion described so far was discovered independently by different researchers using different techniques, separated from each other by decades or centuries. Nobody set out with a grand plan to discover a hierarchy of nested motions, spin within orbit within galactic circuit. Each discovery simply solved whatever specific, immediate puzzle happened to be in front of the people making it. The wobble of a pendulum, the shift of starlight, the drift of a stellar neighbourhood. Only in hindsight, once enough of these individually modest discoveries had accumulated, did the larger pattern become visible. A universe built out of motion nested inside motion, all the way up, with no layer yet found that could honestly be called the final, resting one. There's a specific kind of patience this whole subject seems to demand of anyone studying it closely, a patience worth naming before moving forward into the next, considerably larger discovery. Every layer described in this exploration so far took years, sometimes decades, of careful, repeated measurement before the scientific community accepted it as established rather than merely proposed. The Earth's spin, obvious once demonstrated, was nonetheless resisted for centuries beforehand. The Sun's galactic orbit required generations of steadily improving stellar measurements before its size and duration could be pinned down with any real confidence. Nothing about this subject rewards impatience. Every number quoted so far represents the settled endpoint of a process that, at the time it was actually happening, felt considerably less certain, considerably more contested than the tidy, confident figures now quoted in any modern textbook. The resistance to the idea that the Earth itself was moving, rather than sitting fixed at the centre of everything, wasn't simply stubbornness either. And it's worth being fair to the people who held that older view for as long as they did. Without instruments sensitive enough to detect the subtle shifts in starlight that would eventually confirm the Earth's motion directly, the older, geocentric picture actually accounted for the available evidence reasonably well for a surprisingly long stretch of history. It took not just a bold new idea, but centuries of steadily improving instruments before the accumulated evidence became overwhelming enough to force a genuine change in the consensus picture. That pattern, a strange claim, resisted reasonably at first, eventually settled by evidence too consistent to keep dismissing, shows up again and again throughout the rest of this exploration, and it's worth keeping in mind as the scale of what's being discussed continues to grow. The discovery starts, as these things often do, with a measurement that refused to come out clean. In the 1960s, scientists confirmed the existence of a faint bath of microwave radiation filling the entire sky, leftover heat from the early universe, cooled over billions of years into a whisper just a few degrees above absolute zero. This afterglow, called the cosmic microwave background, was supposed to look the same in every direction. A smooth, uniform temperature no matter which way an instrument happened to be pointed, because in the early universe, the physics producing this glow was expected to be essentially the same everywhere at once. For the most part, that's exactly what it looked like. Smooth. Even. Almost suspiciously uniform, in fact, once instruments got sensitive enough to actually check. Except for one thing that kept showing up, no matter how the measurement was repeated, no matter which instrument or which team ran the check. One direction of the sky read very slightly warmer than the opposite direction. Not by much. A few thousandths of a degree, an amount so small it would have been easy to write off as instrument error, background noise, some flaw in the calibration nobody had caught yet. It didn't go away. Every time the measurement was refined, the same lean showed up again, warmer on one side of the sky, cooler on the exact opposite side, split almost perfectly down a line running through the whole observable universe. Nobody had gone looking for this. It found the people looking for something else entirely, the way the most interesting scientific discoveries often do, arriving as an inconvenience before anyone recognized it as a clue. Early proposals for what might be causing the lean weren't limited to the explanation that eventually won out. Some researchers initially wondered whether the effect might be an artifact of the instruments themselves, some subtle asymmetry in how the detectors were built or calibrated, rather than a genuine signal from the sky. Others considered whether it might reflect some genuine unevenness in the early universe itself, a real physical difference between one direction and another, baked into the structure of the cosmos from its very beginning, rather than something introduced afterward by an observer's own motion. Ruling out these alternative explanations took years of careful, repeated measurement across multiple independent instruments, each new confirmation narrowing the possibilities until the motion-based explanation stood as the only one still consistent with every subsequent test thrown at it. The measurement was eventually confirmed with far greater precision by a dedicated satellite launched in the late 1980s, built specifically to map the cosmic microwave background across the entire sky with a level of accuracy ground-based instruments had never been able to reach. That satellite's data confirmed, beyond reasonable doubt, that the lean wasn't a fluke of any particular instrument or any particular team's methodology. It was real, it was consistent, and it needed an actual physical explanation rather than a footnote about calibration error. 2 later missions pushed the precision even further, each one an improvement on the instrument that came before it, mapping the same underlying pattern with steadily increasing sensitivity across the following decades. The most recent of these missions, launched in the early 2000s, produced a map so detailed that the dipole signature, along with much finer structure sitting on top of it, could finally be measured to a level of precision that would have seemed implausible to the researchers who first stumbled onto the anomaly decades earlier. What began as an inconvenient wobble nobody could quite explain away had become, by the time the most recent instruments finished their work, one of the most precisely measured features in all of observational cosmology, its magnitude and direction pinned down to a degree of confidence that leaves essentially no room left for the original skepticism that greeted it. Each successive mission also had to solve a genuinely difficult technical problem specific to measuring something this faint. The instruments involved need to be cooled to temperatures only slightly above absolute zero themselves, because any warmth in the detector's own components would otherwise swamp the impossibly faint signal they're trying to measure. a whisper of leftover heat from an event that happened billions of years ago, competing against the ordinary thermal noise generated by the measuring equipment's own electronics. Solving that problem required increasingly sophisticated cooling systems, shielding, and orbital positioning, placing each successive satellite further from Earth's own heat and radio interference in a stable orbital position chosen specifically to keep the instrument as cold and undisturbed as physically possible for years at a stretch. By the time the most recent of these missions completed its survey, the measured speed of our motion relative to the cosmic microwave background had been pinned down to a precision of better than 1%, an extraordinary level of confidence for a measurement describing something this abstract, this far removed from anything a person could ever directly confirm through ordinary observation. The direction too had been narrowed down to a comparably tight range, a specific patch of sky rather than a loose general region, precise enough that later researchers searching for the Great Attractor knew almost exactly where to point their instruments, rather than having to scan a broad, uncertain swath of sky, hoping to stumble across the right spot by chance. Here's what that clue turned out to mean. Once enough people had stopped assuming it was a mistake and started asking what could actually produce it. Heat, in this particular context, isn't quite the right word, even though it's the one that gets used. What's actually being measured is something closer to a signature left behind by motion itself, the same basic effect that changes the pitch of a passing ambulance, depending on whether it's approaching or pulling away. Light behaves in a related way. Move toward a source of light fast enough, and the light reaching you gets very slightly shifted toward higher energy, read in this context as very slightly warmer. Move away from a source at the same speed, and the opposite happens, a very slight cooling, the light stretched out just enough to register as a fractionally lower temperature. The comparison to sound is useful precisely because the underlying mechanism, while not identical in its physical detail, produces a structurally similar result. An ambulance siren doesn't change pitch because the ambulance itself is doing anything different. It changes because your own position relative to the source of the sound is changing, compressing sound waves in front of the approaching vehicle and stretching them out behind it. Light, crossing the much larger distances involved in this particular measurement, undergoes a version of the same compression and stretching, driven not by sound waves, but by the underlying wavelength of the light itself, shortened and shifted toward the blue end of the spectrum when the motion is toward the source, lengthened and shifted toward the red end when the motion is away from it. In the specific case of the cosmic microwave background, that shift shows up as an extremely small difference in measured temperature, rather than a difference in visible color, but the governing physics is the same family of effect either way. Independent confirmation of this particular direction came later, from an entirely separate line of evidence that had nothing to do with the cosmic microwave background at all. Surveys measuring the motion of galaxy clusters directly, using their own individual light output rather than any ancient background radiation, arrived at a heading remarkably close to the one derived from the microwave measurement, a genuine cross-check between two methods that had no reason, on their own, to agree unless both were picking up on the same real underlying motion. That agreement mattered enormously to the credibility of the whole picture. Two entirely separate techniques, built on entirely separate physical principles, converging on the same rough answer is exactly the kind of confirmation that turns a strange anomaly into an accepted, well-supported feature of how our particular corner of the universe actually behaves. It helps to picture this a little more concretely than the raw physics alone tends to convey. Imagine standing in a very light, very even rain, falling perfectly straight down, no wind, no direction to it at all. Now start walking forward. Immediately, without the rain itself changing in any way, it starts to feel like it's coming at you from slightly ahead, striking your front more than your back, simply because your own forward motion is carrying you into raindrops that would otherwise have fallen harmlessly past you. Turn around, walk backward instead, and the rain now seems to come more from behind. The rain never changed. Only your motion through it did, and that motion alone was enough to make an otherwise perfectly even shower feel directional, heavier from one side than the other. Extend that same image a little further, and the comparison starts to map onto the actual measurement even more precisely. Walk faster, and the apparent difference between the rain ahead of you and the rain behind you grows more pronounced, the faster walker experiencing a more lopsided version of the same even downpour than the slower walker beside them. The size of the lopsidedness, in other words, carries information about speed, not just direction. Applied to the cosmic microwave background, this is exactly how astronomers extracted an actual velocity, not just a heading, from the size of the measured temperature difference between one side of the sky and the other. A larger measured difference implies faster motion. A smaller one implies slower motion. The rain, or in this case the ancient radiation, becomes a kind of speedometer, provided you know how to read the lopsidedness it produces correctly. The cosmic microwave background works on the same basic principle, just replacing raindrops with ancient radiation and replacing walking speed with a speed considerably harder to picture honestly. The background, as far as anyone can tell, really is close to perfectly uniform, exactly as the early theory predicted. The lean was being introduced afterward by whoever happened to be doing the measuring. Us, Earth, the entire solar system. Moving through this ancient bath of radiation, fast enough that the direction we're heading toward reads slightly warmer, and the direction we're leaving reads slightly cooler. The same way running through falling snow makes the flakes ahead of you seem to come faster, and the flakes behind you seem to lag, even though the snow itself is falling evenly in every direction. This is, as far as anyone has been able to determine, one of the most direct pieces of evidence available for a motion too large to feel, too slow to notice, and too enormous to have been guessed at from any observation made entirely from the ground. The sky itself, read carefully enough, keeps an actual record of which way we're heading, written not in visible light but in the oldest light there is, the leftover glow from an event that happened before stars, before galaxies, before anything resembling the structure of the universe you'd recognize today. There's a deeper principle sitting underneath this whole discovery, one worth naming explicitly, because it connects everything covered in this exploration back to a single, unifying idea that runs through modern cosmology as a whole. Since the 17th century, one of the quiet working assumptions guiding astronomy has been that our own vantage point in the universe isn't special, that whatever physical laws and general conditions apply here apply everywhere else too, and that any observer anywhere else in the cosmos, looking at their own surroundings, would find a universe that looks broadly similar to the one we observe from here. This assumption, sometimes called the Copernican principle, after the astronomer whose work first displaced Earth from the centre of everything, has been tested again and again across nearly every domain of astronomy, and has held up remarkably well each time. The cosmic microwave background dipole represents both a confirmation and a subtle complication of that same principle. On one hand, the underlying background itself really is, once our own motion is properly subtracted out, extraordinarily uniform across the entire sky, exactly what the Copernican principle would predict for a universe without any special privileged locations. On the other hand, the very fact that we can detect our own motion at all, by finding a lean in the otherwise uniform background, confirms that we are, in fact, moving relative to the universe's overall average rest frame, caught up in a genuine, measurable current, rather than sitting at some final, motionless anchor point. The principle survives. It simply comes with the added, slightly humbling detail that surviving the principle means accepting that our own motion, rather than the universe's structure, is responsible for the one meaningful asymmetry visible in an otherwise perfectly even sky. The measured speed behind this particular lean comes out to something like 370 kilometers a second, a number that on its own would already be strange enough to sit with for a while. It's worth being precise about what that number actually represents, because it would be easy to mistake it for yet another version of the same orbital speeds already discussed. It isn't. This figure describes the combined net motion of our entire local group of galaxies relative to the average rest frame of the universe itself, the closest thing cosmology has to an overall universal backdrop against which everything else can be measured. It is not a spin. It is not an orbit around any single nearby object. It is a straight-line drift, a genuine heading, aimed at a specific patch of sky and moving away from the opposite patch, distinct from and layered on top of every rotational motion already described. But it isn't a clean, isolated number either. It's the combined result of every layer of motion already discussed, stacked on top of each other: the Earth's spin, the yearly orbit around the Sun, the 220 million year orbit around the galaxy's centre. And underneath all of that, something else entirely, a bulk motion belonging not to the Earth, not to the Sun, but to the entire galaxy itself, carrying everything inside it, including every layer of motion already described, towards some destination nobody had previously had any reason to suspect existed, because once astronomers subtracted out everything already known, the spin, the orbit, the galactic circuit, there was still a leftover motion refusing to be explained by any of it. The galaxy itself was going somewhere, at genuine speed, and whatever it was heading toward had enough mass, sitting somewhere out in the dark, to be quietly directing the motion of an entire galaxy without that galaxy, or anyone inside it, ever having seen so much as a glimpse of what was doing the pulling. Working out the actual direction encoded in that lean was its own separate technical achievement, requiring careful subtraction of the Earth's own orbital motion and the Sun's own galactic motion from the raw measurement, isolating what was left over as the galaxy's own genuine independent heading. Once that subtraction was done carefully enough, the direction pointed toward a particular patch of sky in the general vicinity of two constellations visible from the southern hemisphere, a stretch of sky that, on its own, looked like nothing in particular through an ordinary telescope. Whatever was producing enough gravitational pull to drag an entire galaxy in that specific direction was going to have to be found some other way, because looking directly at the coordinates the math pointed toward revealed, for a long frustrating stretch of research, almost nothing at all. That gap between having a precise direction and actually identifying what sat in that direction is where the next part of this story properly begins. A number and a heading however precisely measured, only tell you that something massive is out there. They don't tell you what it is, how far away it sits, or how it's arranged. Answering those follow-up questions required a completely different set of tools and a considerably longer, more frustrating stretch of research than the relatively clean detective work that had produced the heading itself. There's something worth naming about the peculiar position this discovery placed researchers in during the years between confirming the direction and finally identifying what sat there. They had in effect a confirmed fact without a confirmed cause, a genuine, repeatable, well-measured signal pointing insistently toward a specific patch of sky, with nothing yet found there to justify it. That's an uncomfortable place to sit, scientifically speaking, knowing something is true without yet knowing why. And it's worth appreciating how much patience that discomfort demanded from the researchers who spent years chasing down an explanation for a signal they already trusted completely. It's a peculiar kind of confidence, trusting a measurement fully while still lacking any physical explanation for what's producing it. Most scientific discoveries move in the opposite order, a candidate explanation proposed first, then tested against the data to see whether it holds up. Here, the data arrived first, confirmed repeatedly, trusted completely, years before anyone could point to the specific object responsible for it. That reversed order, effect confirmed before cause identified, turns out to be a recurring feature of this entire field of research, showing up again in the story of the Great Attractor itself, and again later in the story of the residual motion still unresolved even now. It's worth pausing to appreciate how fragile this whole chain of reasoning could have been, and how solid it actually turned out to be instead. A measurement this small, a few thousandths of a degree spread across the entire sky, is exactly the kind of signal that ordinarily gets buried under instrumental noise, atmospheric interference, and simple measurement error. It survived, repeatedly, across multiple independent instruments, built by entirely separate teams using entirely separate methods, precisely because it wasn't noise. Noise doesn't reproduce itself faithfully across independent experiments built years apart by people who've never spoken to each other. A genuine physical signal does, and this one, checked and rechecked across decades, kept doing exactly that. Finding whatever was doing the pulling turned out to be far harder than detecting that a pull existed in the first place, and the reason for that difficulty is almost comically inconvenient, given how much depends on it. Our own galaxy, the Milky Way, is a flattened disk, densely packed with stars, gas, and dust along its central plane. When astronomers look in certain directions toward the thick middle of that disk, their view of everything beyond it, every distant galaxy, every faraway structure that might otherwise explain what's tugging on us, gets blocked almost completely, drowned out by the glow and obscuring dust of our own galaxy's crowded interior. This blocked region even has an official name, one that sounds more like something from a spy novel than a scientific term: the zone of avoidance. The stretch of sky so thick with foreground material that observing anything behind it, using ordinary visible light, is close to hopeless. The zone of avoidance isn't a small inconvenience either. Depending on the exact wavelength being used and the exact sensitivity of the instrument, it can block out somewhere between 1/10 and 1/5 of the entire sky. A genuinely substantial fraction of the total observable universe, rendered essentially inaccessible to ordinary optical astronomy, simply because our own galaxy happens to sit directly in the way along that particular band. And it just so happens, with a kind of cosmic bad luck that took decades to fully appreciate, that the direction the pull seemed to be coming from sat almost directly behind that obscured stretch of sky. Whatever was doing the pulling was hiding, not through any deliberate concealment, but through sheer geometric coincidence, directly behind the one part of the sky our own galaxy makes hardest to see through. For years this meant the attractor could be measured only by its effect, never by direct observation. Astronomers could track how galaxies in the surrounding region were moving, could measure the speeds and directions of that motion, and could infer from the pattern those motions made that something enormously massive had to be sitting in a particular spot to produce exactly this kind of pull on exactly this many galaxies across exactly this much surrounding space. But looking directly at the spot itself through ordinary telescopes revealed almost nothing but the obscuring haze of our own galaxy's disk, foreground stars and dust standing in for whatever actually lived behind them. Eventually, using instruments capable of seeing in wavelengths that dust and gas don't block as effectively, infrared and radio observations that can look straight through the kind of haze that stops visible light cold, astronomers managed to partially map what was actually sitting in that blocked patch of sky. Infrared light in particular passes through dust far more easily than visible light does, the same basic reason a thick fog dims ordinary headlights, far more than it dims the longer wavelength beams used in certain kinds of specialized fog lamps. By switching to instruments tuned specifically to these longer wavelengths, researchers were able to start picking out individual galaxies sitting behind the obscuring band, one dim smudge at a time, gradually building up a partial census of a region that had previously been treated as an unavoidable blind spot. Dedicated survey projects were eventually built specifically to push this partial census further, systematically scanning the zone of avoidance in near-infrared wavelengths, cataloguing thousands of galaxies that had simply never appeared in any earlier optical survey, because their light, at visible wavelengths, had been thoroughly absorbed and scattered by the intervening dust before it ever had a chance to reach any telescope on Earth. These surveys gradually filled in what had been, for decades, a genuine hole in the map of the surrounding universe, confirming that the region did indeed contain the kind of galaxy density needed to produce the observed gravitational pull, even if a complete, fully detailed census remains, even now, a work in progress rather than a finished undertaking. Radio astronomy contributed its own separate piece of this puzzle, using an entirely different part of the electromagnetic spectrum that passes through, obscuring dust even more readily than infrared light does. Neutral hydrogen gas, the raw material out of which most galaxies are built, emits a very specific, well-known radio signal, one that radio telescopes can detect essentially undimmed by the kind of dust that blocks visible and even much infrared light. Dedicated radio surveys aimed directly at the zone of avoidance picked up this signal from galaxy after galaxy, sitting behind the obscuring band, effectively producing a map of where galaxies actually sit in that hidden region, built entirely without ever needing to see a single one of them in ordinary visible light. Combining this radio data with the earlier infrared surveys gave researchers, for the first time, something approaching a genuine, if still incomplete, three-dimensional picture of what had for so long simply been treated as an unavoidable blank patch, stamped across roughly a fifth of the observable sky. What they found was a substantial concentration of galaxies, an entire supercluster's worth of mass, sitting roughly 250 million light-years away in a region now generally called the Great Attractor, a name given before anyone had confirmed exactly how much mass was there, or exactly how it was distributed. A name that stuck regardless, because it captured, plainly enough, what the thing was doing whether or not its full shape had yet been mapped. The mass required to produce the observed pull is genuinely enormous, equivalent to many thousands of galaxies, concentrated in a way that reaches out across tens of millions of light-years, tugging not just on our own galaxy, but on an entire surrounding neighborhood of galaxies, all being drawn slowly over cosmic timescales toward the same general point in space. The original research establishing this pull came from a team of 7 astronomers working together in the mid-1980s, systematically measuring the motions of hundreds of galaxies across a wide stretch of sky, and finding to their own initial surprise that those motions weren't random. They pointed consistently toward a common direction, a pattern that could only be explained by assuming some large unseen mass was sitting in that direction, pulling on everything nearby. The team's own informal nickname for themselves, borrowed half-jokingly from a well-known film about a group banding together against a larger threat, stuck in the scientific literature almost as firmly as the name they gave the discovery itself, a small human footnote attached to a finding that would go on to reshape how astronomers thought about the motion of galaxies on scales far beyond anything previously mapped with this level of coordinated detail. The specific technique this team used, sometimes called the fundamental plane method, relied on a subtle but reliable relationship between a galaxy's size, its internal rotation speed, and its overall brightness. One well calibrated enough to let researchers work out a galaxy's true distance, independent of how fast it appeared to be moving. Comparing that independently calculated distance to the galaxy's observed redshift, the same basic principle already discussed elsewhere in this exploration revealed a peculiar velocity for each individual galaxy in the survey, a genuine motion layered on top of the universe's ordinary expansion. Doing this for hundreds of galaxies spread across a wide enough stretch of sky was what first revealed the coordinated non-random pattern that eventually pointed toward the hidden mass sitting behind our own galaxy's obscuring disk. I want to be careful here, because it would be easy to make this sound tidier than it actually is. Even now, the Great Attractor isn't fully mapped in the way a nearer, less obscured structure would be. Estimates of its exact mass, its exact distance, its exact shape have shifted over the decades as better instruments and better techniques have chipped away at the same stubborn patch of blocked sky. Some researchers have suggested the Great Attractor isn't really a single unified structure at all, but rather a loose collection of several distinct galaxy clusters happening to sit in roughly the same direction, their combined gravitational effect only appearing, from our particular vantage point, to behave like a single unified attractor. What hasn't shifted is the basic fact of its existence, confirmed independently by multiple different lines of evidence, even while the fine details remain a genuine ongoing subject of research rather than a fully settled account. This particular disagreement over whether the Great Attractor is one structure or several overlapping ones viewed along a single line of sight matters more than it might initially seem, because it touches on a genuinely difficult problem in observational astronomy called projection. Looking out into space along any single direction inevitably stacks together objects sitting at wildly different actual distances from each other, simply because they happen to appear, from our vantage point, along the same line of sight. Two galaxy clusters separated by tens of millions of light-years in actual physical distance can appear, in a two-dimensional image of the sky, to be sitting right on top of each other, their true separation only becoming apparent once careful distance measurements are made for each one individually. Untangling how much of the Great Attractor's apparent mass belongs to one true underlying structure, and how much is an illusion created by several separate structures happening to line up along the same direction, remains one of the more technically demanding aspects of continuing research into the region. There's something worth sitting with in the fact that one of the most influential single objects known to be shaping the motion of our entire galaxy sat, for the better part of a century, essentially unseen, inferred entirely from its effects on everything around it, its actual presence confirmed only once instruments existed capable of looking through the one part of the sky, specifically arranged, by pure coincidence of angle and position, to hide it. For the researchers actually working on this problem across those decades, the experience must have carried its own particular kind of frustration, the sort that comes from being confident something is real without being able to point directly at it. Every other structure in astronomy, up to that point, had eventually yielded to a direct look, given enough time and a large enough telescope. This one simply refused, not because it was too faint or too far, but because of an accident of geometry, a coincidence of angles that placed the one object most responsible for the motion of our galaxy squarely behind the one patch of sky our own galaxy makes hardest to see through. It's a reminder that being right about something and being able to demonstrate it directly are not always the same accomplishment, and that sometimes the gap between the two can stretch on for the better part of a scientific career. It's the kind of discovery that only makes sense in hindsight, once you know to look for it. Before that, it was simply an unexplained pull, a persistent, repeatable anomaly in the motion of galaxies that had no obvious source, hiding this whole time directly behind the one part of the sky nobody could see through. Confirming the Great Attractor's existence answered one question while immediately raising another, the kind of thing that tends to happen throughout the history of this particular line of research. Knowing that something massive sits behind the zone of avoidance, pulling on our galaxy, doesn't by itself explain whether that pull is an isolated event, a single object exerting influence on an otherwise unremarkable surrounding region, or whether it's one visible piece of some much larger, coordinated pattern of motion involving considerably more of the surrounding universe than any single attractor could account for on its own. Answering that follow-up question required an entirely different technique, one that had nothing to do with looking for hidden mass directly, and everything to do with tracking patiently and systematically how a very large number of galaxies were actually moving. This shift in approach, from looking for a single hidden object to tracking the collective behavior of thousands of visible ones, represents a genuinely different way of doing astronomy, one that had only become practical relatively recently. Once telescopes and instruments existed capable of measuring the individual velocity of enough galaxies, spread across a wide enough volume of space to make the resulting statistical picture meaningful rather than merely suggestive. The technique itself would go on to reveal something considerably larger than anyone studying the Great Attractor alone had initially anticipated. Mass estimates for the Great Attractor specifically have shifted more than once since the original discovery, generally trending towards somewhat more modest figures than the earliest calculations suggested, as improved distance measurements and a better understanding of exactly how much of the region's total mass sits in the Great Attractor itself versus in the broader surrounding structure it belongs to, gradually refined the picture. This kind of downward revision isn't unusual in astronomy, and it doesn't undermine the underlying discovery. Early estimates of almost any newly identified structure tend to carry larger uncertainties, generally erring toward larger, more dramatic figures, simply because the observational tools available at the time couldn't yet distinguish cleanly between the structure itself and everything surrounding it along the same line of sight. Once astronomers had a rough sense of the Great Attractor's location and pull, a bigger question opened up almost immediately, one that took considerably more work to answer than finding the attractor itself. Was our galaxy simply falling toward this one structure, in isolation, the way a single object might fall toward a single source of gravity? Or was something larger going on, a whole shared pattern of motion that the Great Attractor was only one visible piece of? The answer came from a technique that has nothing to do with looking at galaxies directly, and everything to do with tracking how they move, Water, left to its own devices, doesn't need to be told which direction is downhill. It simply flows there, following the shape of the terrain, gathering into streams, then into rivers, then into shared basins where multiple streams converge because the underlying landscape happens to funnel them all toward the same low point. Galaxies do something structurally similar, except the terrain they're responding to isn't made of rock and soil. It's made of gravity itself, shaped by where mass happens to be concentrated across enormous volumes of space. Map the velocities of enough galaxies across a wide enough region. Track not just where they are, but which direction and how fast they're each moving, and a pattern emerges that looks remarkably like water finding its way downhill. Streams of galaxies converging along invisible slopes carved by the distribution of mass, gathering, eventually into shared basins the way rivers gather into a common watershed. Building this kind of map is a considerably larger undertaking than it might initially sound. It requires measuring not just the position of each galaxy in a given survey, which is itself difficult enough at these distances, but also its individual velocity, separated out from the general expansion of the universe as a whole, so that what remains is the galaxy's own local motion relative to its immediate surroundings. Multiply that requirement across tens of thousands of galaxies, spread across hundreds of millions of light years, and the scale of the undertaking starts to become clear. Each individual measurement carries its own uncertainty, its own margin of error, and only by combining enormous numbers of these individually imperfect measurements does a genuinely reliable overall pattern begin to emerge. A technique closer to statistical cartography than to any single decisive observation. The specific mathematical technique used to turn all these individual noisy velocity measurements into a single coherent map involves a kind of statistical reconstruction, essentially finding the most probable underlying pattern of mass distribution that would produce the observed pattern of galaxy motions, given everything already known about how gravity behaves at these scales. It's a bit like reconstructing the shape of an entire riverbed by watching where thousands of individual leaves happen to drift on the surface of the water, each leaf's path telling you something small and uncertain on its own. But the combined pattern across thousands of leaves revealing the underlying shape of the channel guiding all of them, a shape none of the leaves themselves could ever reveal in isolation. In 2014, a team of astronomers used exactly this technique, mapping the motions of tens of thousands of galaxies across a truly vast surrounding volume, to chart out the actual boundaries of the basin our own galaxy sits inside. The result was the first real map of a structure now called Laniakea, a name drawn from Hawaiian, meaning something close to immeasurable heaven, chosen deliberately for a structure that, once mapped, turned out to be almost impossible to describe using ordinary comparisons. Before this mapping was done, our galaxy had generally been described as belonging to a smaller structure, informally called the Virgo supercluster, named after the prominent cluster of galaxies sitting at its centre. The new velocity-based mapping revealed that this older picture had actually been describing only the innermost portion of something considerably larger. What had been called the Virgo supercluster turned out to be just one lobe, one arm, of the much more extensive basin the new survey had finally traced out in full, requiring a genuinely new name for a structure whose true extent had never actually been mapped before, even though pieces of it had been individually catalogued for decades under the older, more modest name. Laniakea spans roughly 500 million light-years across and contains something on the order of 100,000 galaxies, our own included, all of them caught in the same broad shared pattern of motion, all of them, in one way or another, being drawn toward the same general gravitational lowland, the same basin, with the Great Attractor sitting as one prominent feature within that basin, rather than as the entire explanation for it. I think what's strangest about this particular discovery isn't the scale, impressive as the scale genuinely is. It's the fact that nobody standing anywhere inside a basin this size would have any obvious way of noticing its edges from the inside. You don't feel a watershed by standing in it. You only see the shape of it by mapping how everything within it moves, from far enough outside to see the whole pattern at once, a vantage point no single observer, standing on a single planet orbiting a single star inside a single galaxy, could ever actually occupy directly. We live, as far as current mapping can tell, roughly in the outer reaches of this particular basin, caught in its gravitational current the same way every other galaxy within its boundaries is caught, moving collectively at a shared drift that has nothing to do with any single galaxy's individual push and everything to do with the shape of the larger structure. All of them happen to be sitting inside our own immediate surroundings well before reaching the scale of Laniakea itself, already involve a smaller version of the same basic pattern, worth mentioning since it's the layer sitting closest to home. The Milky Way belongs to a modest cluster of a few dozen galaxies known as the Local Group, dominated by two large spiral galaxies, our own and a considerably larger neighbour, roughly 2.5 million light-years away, currently approaching us at somewhere around 110 kilometres a second. That approach is real, measured directly through the light of the approaching galaxy itself, shifted toward the blue end of the spectrum in exactly the way this whole exploration has already discussed, and it will, according to current projections, eventually result in the two galaxies merging, billions of years from now, long after the Sun itself has changed dramatically enough that the question will matter to nobody currently alive to worry about it. This smaller, more local drama, one galaxy approaching another within the local group, sits nested inside the much larger drift toward the Great Attractor, which itself sits nested inside the Laniakea basin as a whole, layer after layer, each one operating on its own scale, each one real, each one simultaneously true. There's a genuine technical challenge buried in defining where any one basin actually ends and where a neighbouring one begins. A challenge that mirrors, on a larger scale, the same kind of ambiguity you'd encounter trying to define the exact boundary of a real watershed on uneven terrain. Close to the centre of a basin, the direction of flow is usually unambiguous, everything nearby clearly heading toward the same low point. Near the edges, though, the picture gets muddier. A galaxy sitting close to the boundary between two neighbouring basins might show a velocity that's only weakly aligned with either one, caught in a kind of gravitational tug-of-war between competing lowlands, its ultimate fate genuinely uncertain until enough time passes for the larger scale flow to eventually win out. Some of the uncertainty in exactly how large Laniakea truly is compared to its neighbouring basins comes directly from this ambiguity, a genuine feature of the underlying physics rather than simply a limitation of current measurement technique. Neighbouring basins do exist, incidentally, catalogued by the same broad mapping effort that first identified Laniakea, each one its own, separate collection of galaxies, all being drawn toward their own separate central concentration of mass, entirely independent of whatever collection of galaxies happens to be drawn toward ours. From far enough away, on a large enough map, the whole observable universe would look something like an enormous three-dimensional patchwork of these basins, each one its own quiet drainage system, none of them communicating with each other in any meaningful sense, each one simply following the shape of the gravitational terrain it happens to be sitting inside. Some of these neighbouring basins have been given their own names since the original mapping effort, each one associated with its own central concentration of mass, its own version of a great attractor sitting at the low point of its particular watershed. None of them, as far as current surveys can tell, communicate with each other in any way that affects the actual motion of galaxies on either side, the boundary between neighbouring basins functioning less like a wall and more like a genuine gravitational stalemate, a region where the pull toward one basin's centre roughly balances the pull toward its neighbours, leaving whatever sits along that boundary drifting only weakly in either direction, undecided for as long as the current arrangement of mass on both sides happens to hold roughly steady. It's worth pausing on the timescale involved in actually completing a single journey through this basin, since the numbers involved make the earlier orbital periods discussed in this exploration look almost brisk by comparison. Crossing the full extent of Laniakea from one edge to the other, moving at the basin's own characteristic drift speed, would take on the order of tens of billions of years, a span longer than the current age of the universe itself. Nothing currently inside the basin, including our own galaxy, has completed anything remotely close to a full crossing since the structure first began organizing itself out of the early universe's initial, nearly uniform distribution of matter. Whatever eventual fate awaits everything caught in this particular current lies so far in the future that it's less a prediction about anything anyone could witness, and more a simple statement about the mathematical trajectory the current structure implies, extrapolated forward across timescales that dwarf every other duration mentioned so far in this exploration. That drift, incidentally, comes with a number attached to it, and the number is worth pausing on, because it's the kind of figure that resists intuition the same way most of this exploration has, right from its opening sentence. Our galaxy, along with the entire surrounding portion of Laniakea nearest to us, is moving at somewhere around 600 kilometers a second, relative to the average expansion of the universe as a whole, a bulk motion layered on top of every smaller motion already described, from the planet's spin to the sun's galactic orbit, stacking together into a single combined drift that nobody standing on the ground on any given ordinary evening has ever had the faintest sensation of. For a while, this was treated, reasonably enough, as close to the final word on the subject. Our galaxy sits inside Laniakea. Laniakea drains toward the Great Attractor. The Great Attractor accounts for the observed motion, case closed more or less, pending finer details still being worked out about the exact mass and shape of the attractor itself. It would take a further piece of research, extending the same basic technique out to considerably greater distances, to reveal that even this account, satisfying as it was, still wasn't the complete story. The team responsible for this next extension faced a specific practical challenge worth mentioning. Measuring galaxy velocities reliably becomes progressively harder the further out you look, since the same instruments and techniques that work comfortably within Laniakea's boundaries start running into the limits of their own precision once applied to structures hundreds of millions of light-years further away. Confirming a connection to something as distant as the next structure in this chain required not just extending the survey outward, but improving the underlying measurement technique itself, squeezing more reliable data out of galaxies whose light had travelled considerably further and whose individual velocity signals were correspondingly fainter and harder to isolate from ordinary measurement noise. there's a further wrinkle worth mentioning, one that keeps this particular map from being quite as tidy as a finished watershed diagram might suggest. The boundary of Laniakea isn't a hard edge in the way a real watershed's ridgeline is. It's defined by where the flow of galaxy motions changes character, where galaxies stop clearly favouring our basin's gravitational lowland and start favouring some neighbouring one instead. That transition is gradual rather than sharp, meaning the exact boundary of Laniakea, unlike its interior, remains somewhat softer and more provisional than the confident finished-looking maps published of it might suggest at first glance. I keep coming back to how strange it is that a structure this size, containing our entire galaxy, along with 100,000 others, was only mapped for the first time within living memory, well after most of the other discoveries in this exploration had already settled into textbooks. It isn't that Laniakea only recently came into existence, it's that recognizing its shape required a specific combination of data, enough individual galaxy velocities, measured precisely enough across a wide enough volume, that simply hadn't existed in usable form until relatively recently. The structure had always been there, organising the motion of everything inside it since long before any instrument existed capable of noticing the pattern. What changed wasn't the universe. What changed was our capacity to finally see the shape of something we'd been sitting inside the entire time. The visualizations produced from this mapping since first published have become some of the more widely circulated images in popular astronomy, showing streamlines of galaxy motion curving and converging like a weather map of wind currents, except instead of air pressure driving the flow, it's the underlying distribution of mass across hundreds of millions of light years. Our own position within that flow sits recognizably near one edge of the mapped structure, a small tributary joining a much larger confluence of streams, all bending gradually toward the same broad shared basin, the way tributaries bend toward a river's main channel, long before any of the individual streams could see the river itself. Here's where the story does something that catches most people off guard the first time they hear it, the same way it caught the astronomers who first noticed it, expecting, reasonably enough, that the Great Attractor would turn out to be the end of the explanation rather than another step along the way. It isn't. The Great Attractor itself, that enormous concentration of mass hiding behind our own galaxy's obscuring disk, turns out to be moving too, and not randomly. It's being pulled, in turn, by something even larger, sitting even farther away, a structure massive enough to be tugging on an object that itself contains the mass of thousands of galaxies. That larger structure is called the Shapley supercluster, named after the astronomer who first catalogued concentrations of galaxies in that general region of sky, decades before anyone understood their true scale or significance. The original cataloguing work, done long before the technology existed to appreciate what it had actually found, simply recorded an unusually dense clustering of galaxies in one particular patch of sky, filed away as an interesting regional concentration among many other regional concentrations noted across the same era of systematic sky surveys. It would take the better part of a century and considerably more sensitive instruments before anyone recognized that this particular concentration wasn't just locally dense. It was one of the single largest known structures in the observable universe. The astronomer whose name the structure carries had already built a substantial career studying the scale of our own galaxy decades before this particular catalogue work, having earlier made a name for himself by using a specific class of pulsing star to work out, for the first time, the true size of the Milky Way and our own sun's position well away from its centre, a finding that itself had overturned an earlier mistaken assumption that our sun sat near the galaxy's middle. That same systematic, patient cataloguing habit, applied later in his career to galaxies rather than individual stars within our own, eventually turned up the concentration that would go on to bear his name, decades after the original observations were filed away as a modest regional curiosity, rather than the record holder it would eventually be recognized as. It sits roughly 650 million light-years away, considerably farther than the Great Attractor itself, and it is, by most current estimates, one of the most massive collections of galaxies known to exist anywhere in the observable universe. A supercluster of superclusters, so to speak, dense enough with galaxy clusters that its gravitational reach extends across an almost incomprehensible span of surrounding space. Estimates of its total mass vary depending on the exact method used to calculate it, but most place it somewhere in the range of 10,000 trillion times the mass of the Sun, concentrated across a region spanning several 100 million light-years, making it, by some measures, the single largest concentration of mass in our entire cosmic neighbourhood, dwarfing even the combined mass of everything gathered inside the Laniakea basin. To put that comparison in perspective, Laniakea itself, the basin containing our own galaxy, along with roughly 100,000 others, is being pulled, as a whole, toward a structure whose individual mass estimate exceeds the combined mass of everything currently mapped inside our own basin. The attractor pulling on our attractor isn't merely larger, it may be considerably larger, by a margin substantial enough that describing the relationship as simply bigger risks understating just how lopsided the comparison actually is. It's worth unpacking what the phrase supercluster of superclusters actually means structurally, since it's easy to let a phrase like that slide past without registering its actual implications. An ordinary galaxy cluster contains anywhere from a few dozen to a few thousand individual galaxies, bound together by their mutual gravity into a single, recognizable group. A supercluster, one level up, is a much looser association of many such clusters, spread across tens of millions of light-years, not tightly bound together the way an individual cluster is, but still moving in a broadly coordinated way, influenced by the same underlying larger-scale distribution of mass. The Shapley supercluster represents yet another level higher still, an association of multiple superclusters, each one already containing multiple clusters, each cluster already containing hundreds or thousands of individual galaxies. The structure is, in the most literal sense available, a hierarchy of hierarchies, nested groupings within nested groupings, all the way down to a single star like the Sun, orbiting within a single galaxy, sitting within a single cluster, sitting within a single supercluster, sitting within this vastly larger structure pulling on all of it at once. The relationship between these two structures resembles something closer to a nested set of gravitational wells than a single, simple pull. Our galaxy sits inside the local group, a small cluster of galaxies. The local group sits inside the larger flow toward the Great Attractor, and the Great Attractor itself, along with everything falling toward it, sits inside the still larger gravitational reach of the Shapley supercluster, which is doing to the Great Attractor roughly what the Great Attractor is doing to us, drawing it inward, slowly, patiently, across a timescale that dwarfs anything resembling a human unit of measurement. I find something genuinely disorienting in that arrangement, once it settles in properly. The thing doing the pulling has something pulling on it too. There's no reason, once you notice this pattern, to assume it necessarily stops at the Shapley supercluster either. Follow the direction of any single attraction far enough, and there's a reasonable chance it stops being the end of the story and starts looking, instead, like a waypoint, caught in the gravity of something larger still, sitting even further out, patient in a way that makes every nearer pull look almost modest in comparison. It's worth pausing on just how differently these two structures relate to each other, compared to how a planet relates to a star, or a star relates to a galaxy's centre. A planet orbits a star in a comparatively tidy, well-defined ellipse, a relationship stable enough to predict centuries in advance with remarkable precision. The relationship between the Great Attractor and the Shapley supercluster is nothing like that tidy. It's not an orbit in any conventional sense. It's closer to a slow, gravitational lean, an entire supercluster's worth of galaxies drifting collectively in a general direction, without any of the clean periodicity that governs a planet's yearly circuit. The timescale involved is long enough, and the structures involved are complex enough, that describing this relationship as an orbit would suggest a tidiness the actual physics doesn't really have. This isn't an infinite regress in any technical sense, and I want to be careful not to overstate what's actually known here. At the very largest scales, the universe is thought to be, on average, close to uniform, without some single ultimate attractor sitting at the centre of everything, pulling all matter toward one final destination. The very largest surveys of galaxy distribution, spanning billions of light years rather than hundreds of millions, do eventually show a genuinely even, statistically uniform spread of matter, with no single structure massive enough at that scale to organise the motion of everything around it the way the Great Attractor and the Shapley supercluster organise motion at the comparatively local scale this exploration has been operating at. But locally, on the scale of hundreds of millions of light years, the scale this whole exploration has been operating at, the pattern of nested pulls, basin within basin, attractor within larger attractor, does appear to hold, at least as far out as current mapping has managed to reach, confirming that the Shapley supercluster genuinely exerts this kind of pull, rather than simply sitting in the same rough direction as the Great Attractor by coincidence, required extending the same velocity mapping technique used to chart Laniakea out to considerably greater distances, tracking the motion of galaxy clusters far beyond our own basin's boundary, and checking whether their individual drifts pointed consistently toward the Shapley region. They did, with enough consistency across enough independent clusters that the connection is now treated as well established within the field, even though, as with the Great Attractor before it, the fine details of exactly how much of the total pull Shapley accounts for versus how much comes from other, less individually prominent structures scattered across the same general direction, remains an area of continuing refinement. What that means, practically, is that the motion carrying our galaxy right now isn't simply a straight line toward a single fixed point. It's closer to a current within a current, a smaller flow nested inside a larger one, both of them moving in roughly, though not perfectly, the same overall direction, compounding into a single combined drift whose ultimate cause, even now, isn't fully and completely resolved. For a while, once the Shapley connection was established, this too felt close to a satisfying, complete answer. Our galaxy, pulled toward the Great Attractor, itself pulled toward Shapley, a clean two-step chain accounting for the full observed motion. It would take one more round of careful measurement, comparing the total predicted pull from every mapped structure against the actual observed speed and direction, to reveal that even this two-step chain didn't quite balance the books. Something, once again, remained unaccounted for, a residual discrepancy small enough to have been easy to dismiss at first, and persistent enough across repeated independent checks that dismissing it eventually stopped being the responsible option. That pattern, satisfaction, followed by a newly discovered gap, followed by a search for whatever might close it, repeats often enough across this entire exploration that it starts to feel less like a series of separate surprises and more like the basic operating rhythm of this whole field of research. Every time the account seems complete, a slightly more careful measurement reveals it wasn't quite complete after all, not through any failure of the earlier work, but simply because each new layer of precision reveals a slightly finer discrepancy the previous generation of instruments hadn't been sensitive enough to catch. Whatever this final discrepancy turns out to mean, it's worth sitting with the fact that finding it required successfully completing every earlier step first. Nobody could have noticed the residual gap without first confirming the Great Attractor, and nobody could have confirmed the Great Attractor without first noticing the cosmic microwave background's subtle lean. Each discovery in this chain depended entirely on the one before it, a genuine cumulative structure of understanding built one confirmed layer at a time, none of it skippable, none of it achievable out of order. I want to be honest about where the confident part of this story actually ends. The existence of the Great Attractor, confirmed independently multiple times over. Its rough mass and location, reasonably well established if still somewhat imprecise given the obscuring dust it sits behind. Laniakia's existence as a basin, confirmed by the 2014 mapping and subsequent refinements. The Shapley superclusters pull on the Great Attractor, measured and consistent with the observed motion. What's considerably less settled is whether this entire chain, attractor within basin, within larger attractor, actually accounts for the full observed speed and direction of our galaxy's motion, or whether something further out, something not yet mapped, not yet identified, still needs to be added to the account. That question turns out to be the genuinely open one, the one current research hasn't fully closed, and it's worth sitting with honestly rather than smoothing over for the sake of a tidier story. There's a particular kind of intellectual vertigo available in tracing this chain all the way from a single planet to a structure spanning hundreds of millions of light years. One distinct from the earlier vertigo of simply learning you're moving faster than you'd ever imagined. This is less about speed and more about scale of consequence, the recognition that the same basic force, gravity, operating according to the same basic rules discovered centuries ago by watching apples fall and planets orbit, scales up, without needing any new physics, into structures organizing the motion of 100,000 galaxy basins across 500 million light-years. Nothing exotic had to be invented to explain any of this. The same force holding you to your chair right now is the force responsible for every layer of this entire nested hierarchy, all the way out to the largest structure covered in this exploration. Here's where the story stops being a tidy chain of nested discoveries and starts becoming something considerably messier. The part current research hasn't managed to close out cleanly, no matter how many additional structures get mapped and added to the account. Add together everything currently known to be pulling on our galaxy, the Great Attractor's contribution, the larger pull from the Shapley supercluster sitting behind it, every other smaller structure that's been identified and factored into the calculation since the original mapping was done. Run the numbers, and the combined effect of all these known, mapped, reasonably well understood sources of gravity should produce a specific, predictable, total speed and direction for our galaxy's motion through the universe. It doesn't quite match. The actual measured speed and direction, the one derived independently from the cosmic microwave background's lean, comes out slightly different from what the known, mapped attractors alone would predict. Not wildly different. Not different enough to suggest something has gone catastrophically wrong with the whole picture built up so far, but different enough and consistently enough across multiple independent studies that it can't simply be waved away as measurement noise either. Something is missing from the ledger. That's the honest, unglamorous way to put it, and it's worth sitting with plainly before reaching for anything more dramatic. A straightforward accounting exercise, add up the known pulls, compare to the observed motion, comes up short, and the shortfall has to be explained somehow. It's worth being clear about how this shortfall gets calculated in the first place, since the number itself depends on a chain of earlier measurements, each carrying its own uncertainty. Researchers start with the observed bulk motion, derived from the cosmic microwave background dipole, and cross-checked against independent galaxy surveys. From that total, they subtract the calculated gravitational contribution of every mapped structure within the relevant volume, the Great Attractor, the Shapley supercluster, and a range of smaller, less individually famous concentrations of mass that also contribute modestly to the overall pull. What remains after that subtraction is the residual, the part of the motion current models cannot yet explain by pointing to any specific located structure. The size of that residual, and how seriously to take it, depends heavily on how confidently each of the earlier subtracted contributions has itself been measured, which is precisely where the disagreement between different research groups tends to concentrate. There are a few different ways this particular gap gets talked about, depending on which researcher you happen to be listening to, and the disagreement itself is worth understanding honestly rather than glossed over in favour of a single confident answer. One camp treats the discrepancy as fundamentally mundane, a problem of incomplete mapping rather than missing physics. On this view, the shortfall exists simply because our current survey of galaxy clusters and superclusters, however impressive, still hasn't managed to fully catalogue everything sitting within the relevant volume of space. There could easily be additional structures, comparable in scale to the ones already identified, sitting in regions still poorly surveyed, whether because they're obscured by dust the way the Great Attractor once was, or because they're simply too faint, too distant, or too recently formed to have made it into current catalogues yet. Under this reading, the missing piece is a bookkeeping problem, solvable in principle, waiting on better instruments and more complete surveys to finally close the gap. Measuring this kind of bulk motion at all requires a particular technique worth understanding, because the difficulty of the measurement is a large part of why the debate has stayed unresolved for so long. Researchers look at a particular class of exploding star, one whose peak brightness follows a reliable, well-calibrated pattern, allowing its true distance to be worked out independently of how it appears to be moving. Compare that calculated distance to the star's observed redshift, the amount its light has been stretched by the expansion of the universe, and any leftover discrepancy between the two reveals a genuine physical motion layered on top of the universe's ordinary expansion, a peculiar velocity, in the technical language of the field, distinct from the expansion itself. Do this for enough individual exploding stars, spread across a wide enough stretch of sky and a wide enough range of distances, and a pattern of bulk motion begins to emerge. Galaxy clusters at vastly different distances, all showing a coordinated drift in roughly the same direction, more coordinated than ordinary random motion alone would produce. The other camp takes the discrepancy more seriously, as a potential signal of something genuinely unaccounted for by current models, a residual motion that might not be explainable simply by finding one more supercluster hiding behind one more patch of obscuring dust. This more provocative reading picked up a name of its own in some corners of the research literature. Dark flow, a deliberately evocative term for a bulk motion that, on this interpretation, might be responding to mass sitting entirely outside the observable universe altogether, structures so far away that light from them hasn't had time to reach us yet, exerting a gravitational pull whose effect crosses that boundary, even though the light carrying direct evidence of the structures themselves never has. The original claim, when it was first published in the late 2000s, used a related but distinct technique, one that doesn't rely on exploding stars at all. It looked instead at how the cosmic microwave background's light gets very slightly altered as it passes through the hot, ionized gas sitting inside massive galaxy clusters, an effect that shifts the background's apparent temperature in a way that depends on how fast the cluster itself is moving relative to that background radiation. Tracking this specific effect across a large sample of distant galaxy clusters, spread across a wide swathe of sky, revealed a coordinated drift that appeared to extend to distances considerably farther than any known structure, including the Shapley supercluster, could plausibly explain on its own. The finding generated an immediate wave of attention, precisely because of how strange its implications were if taken at face value, and an almost equally immediate wave of technical scrutiny from other researchers eager to check whether the signal would survive closer examination. I want to slow down on that claim specifically, because it's the kind of statement that sounds, on first hearing, almost too strange to take seriously, and it deserves to be handled with exactly the caution that strangeness warrants. The observable universe has a genuine physical boundary, the furthest distance light has had time to travel since everything began. Nothing beyond that boundary can be seen, measured, or directly confirmed by definition, because no light from it has ever reached us, and none ever will, not for a very long time yet. If the missing gravitational pull genuinely originates from structures sitting beyond that boundary, we are, in this one very specific and very strange sense, being tugged by something that is, and will likely remain, permanently invisible to any instrument built by anyone, ever, regardless of how sensitive that instrument eventually becomes. That's a genuinely different category of unknown than anything else covered so far in this exploration. The Great Attractor was unknown because of an obscuring cloud of dust sitting in the way, a practical, solvable problem that better instruments eventually cracked open. Structures potentially responsible for the dark flow residual, if the more provocative interpretation turns out to be correct, would be unknown for a reason no future instrument could ever fix. A limit built directly into the geometry of an expanding universe, rather than a limit imposed by any particular technology's current shortcomings. I don't think it would be honest to present this as a settled matter in either direction. The dark flow hypothesis, when it was first proposed, generated a considerable amount of excitement and an almost equal amount of skepticism, and that split has never fully resolved in the years since. Some subsequent studies, using different techniques and different data sets, found evidence broadly consistent with an unexplained residual motion along similar lines to what was originally reported. Other studies, using their own independent methods, found the original signal weaker than initially claimed, or attributable, at least in part, to statistical artifacts and known sources of contamination in the data, rather than to any genuinely new physical effect. The disagreement between these studies isn't a matter of one side being careless and the other careful. It reflects a genuinely difficult measurement, operating at the very edge of what current instruments can reliably detect, where small differences in methodology can meaningfully shift the conclusion one way or the other. It's worth stepping back to note what this kind of open disagreement actually says about the broader field, since it would be easy to read a genuine scientific dispute as evidence that the underlying science is somehow shaky or unreliable. The opposite is closer to the truth. The fact that researchers can disagree this specifically, pointing to precise numerical thresholds, precise statistical techniques, precise data sets, and precise sources of potential contamination, reflects a field mature enough to argue about genuinely fine details rather than basic fundamentals. Nobody in this debate doubts that the universe is expanding, or that galaxies have real, measurable peculiar velocities, or that gravity is the force responsible for organizing matter into the kinds of structures already described throughout this exploration. The disagreement concerns a comparatively narrow technical question, sitting right at the frontier of what current instruments can measure with confidence, which is exactly where genuine scientific disagreement is supposed to live. Later, more sensitive full-sky surveys of the cosmic microwave background revisited the same underlying question with considerably better data than had been available for the original claim, and their conclusions landed closer to the more conservative reading, finding the residual signal, once every known source of contamination was carefully subtracted out, to be smaller and less statistically overwhelming than the original result had suggested. That doesn't fully settle the matter either. Measurement techniques in this particular corner of astronomy have continued to improve since those follow-up studies, and the specific question of exactly how large the unexplained residual motion actually is, once every known structure is properly accounted for, remains an active area of ongoing observational work rather than a fully closed book. There's a broader pattern worth noticing here, one that shows up repeatedly across the history of this kind of research. Bold, provocative claims, the sort that suggest something genuinely strange is happening, tend to generate intense initial excitement, followed by an equally intense period of scrutiny, followed in many cases by a settling toward a more modest, though not necessarily zero, version of the original claim. This isn't a story of science failing or overreaching. It's closer to how science is actually supposed to work. Provisional claims tested repeatedly against new data, refined, narrowed, sometimes discarded entirely, until whatever survives that process earns a level of confidence the original announcement, however exciting, hadn't yet earned on its own. The dark flow claim sits right now somewhere in the middle of that process, neither fully vindicated nor fully discarded, a genuinely live question rather than a settled answer in either direction. It's also worth mentioning honestly that some researchers have proposed explanations for the residual that don't require reaching beyond the observable universe at all, nor do they require simply waiting for better surveys to find more ordinary structures. A few have suggested the discrepancy might partly reflect subtle systematic errors in how certain distance measurements are calibrated, errors that could, in principle, be corrected through improved technique rather than through discovering any new structure or invoking any exotic explanation whatsoever. Others have pointed to the statistical challenge of measuring bulk flow at all across such vast distances, where the number of independent, reliable data points remains genuinely limited, making it difficult to distinguish a true signal from a chance alignment of otherwise unremarkable individual measurements. Each of these more mundane explanations remains on the table alongside the more provocative ones, and current research hasn't yet definitively ruled any of them out. It's worth remembering that cosmology has resolved comparably strange-sounding puzzles before, puzzles that once seemed to demand an exotic explanation, before more careful measurement eventually settled on something considerably more mundane. Early measurements of the universe's expansion rate, for instance, once diverged wildly enough between different research groups to suggest the universe might be younger than some of the stars inside it, an apparent contradiction that generated real concern before improved instruments and improved technique eventually narrowed the disagreement down to something consistent and sensible. There's no guarantee the current motion discrepancy will resolve the same way, toward the mundane explanation rather than the exotic one, but the history of the field offers a reasonable basis for patience, a track record of genuinely strange-looking puzzles eventually yielding to better data, more often than not, without requiring anything as dramatic as the most provocative available reading. What nobody seriously disputes across either side of this particular debate is that the basic discrepancy exists at some level. The known mapped attractors do not by themselves fully account for the observed motion. Where people disagree is on how large that unexplained portion actually is once every known source of measurement error and incomplete mapping has been properly subtracted out, and on whether whatever remains, once that subtraction is done as carefully as current techniques allow, is large enough to actually require an explanation reaching beyond the observable universe, or small enough to be comfortably explained by structures simply waiting to be found within it. Newer survey projects still actively gathering data as of this telling aim to extend the same basic velocity mapping technique used for Laniakea out to considerably greater distances than any previous effort has managed, hoping to catch a more complete picture of exactly which structures out to the largest currently observable scales are contributing to the overall pull. If the mundane explanation turns out to be correct, these surveys should eventually locate enough additional ordinary structure to close the gap entirely, folding the residual motion into an expanded, more complete map rather than leaving it as a standing mystery. If the more exotic explanation holds instead, no amount of additional mapping within the observable universe will ever close the gap, because the missing mass, by definition, sits somewhere no survey conducted from here will ever be able to reach. Distinguishing between these two outcomes may simply require watching, patiently, as each new generation of survey data either finds the missing piece or fails to, a process that could plausibly take another decade or more of careful, incremental work before a confident answer emerges either way. I find something worth sitting with in the fact that this particular question remains open rather than being uncomfortable about the lack of resolution. Most of what's been covered in this exploration so far, the Earth's spin, the Sun's orbit, the Galaxy's motion, the existence of the Great Attractor and the Shapley supercluster, represents settled, well-confirmed science, established through repeated independent verification until reasonable doubt was no longer available. This last piece is different. It sits right at the boundary between settled and unsettled, between confirmed structure and genuine ongoing mystery, and that boundary is precisely where active research actually happens, where the interesting work is still being done, rather than in the tidier, more finished parts of the story that already made it into consensus. There's a particular kind of intellectual honesty required to sit with a gap like this without either dismissing it or overselling it. It would be easy to lean hard into the dramatic reading, structures beyond the edge of the observable universe reaching in to tug on our galaxy from somewhere we will never be able to see directly, and treat that as an established fact rather than one serious hypothesis among several competing explanations. It would be equally easy to dismiss the whole question as a minor bookkeeping error destined to vanish once surveys improve, treating a genuinely open scientific question as though it were already closed simply because the mundane explanation happens to be more comfortable. Neither shortcut does justice to where the actual research currently stands. What can be said with confidence is this: our galaxy is moving at a speed and in a direction that has been measured with considerable precision, using multiple independent techniques that agree with each other closely enough to rule out simple measurement error. A meaningful portion of that motion has been successfully traced back to real, mapped, physically confirmed structures, the Great Attractor and the Shapley supercluster chief among them, and a smaller, but real, and so far not fully explained, portion of that same motion remains unaccounted for by anything currently mapped, leaving open the genuine possibility that either our surveys are still incomplete, or that something considerably stranger, something reaching from beyond the edge of what any instrument will ever directly observe, is contributing to the drift as well. Either answer, once it's eventually settled, changes very little about the day-to-day reality already established earlier in this exploration. The galaxy moves. We move with it. The exact accounting, whether it turns out to close cleanly with better surveys or requires reaching for an explanation beyond the observable horizon, doesn't change the basic, already confirmed fact that none of us have ever, for a single moment, actually been standing still. What it does change is how confidently anyone can currently describe the destination. Every structure covered in this exploration turned out, on closer inspection, to be nested inside something larger, pulled by something bigger still, a pattern that seemed, for a while, like it might simply keep going indefinitely, a tractor within a tractor, all the way out. The unexplained residual motion complicates even that pattern, suggesting the full picture might not be a simple, if very long, chain of nested pulls after all, but something with an additional piece nobody has fully identified yet, whether that piece turns out to be an ordinary structure waiting to be mapped or something considerably harder to ever pin down directly. There's a specific kind of scientific honesty at work in ending this particular section without a clean resolution, one worth naming explicitly rather than leaving implicit. It would have been easy to simply omit this unresolved piece entirely, presenting only the tidier, fully confirmed portions of the story: the Earth's spin, the Great Attractor, Laniakea, Shapley, and stopping there, leaving the impression of a complete closed account. That would have been a more comfortable story to tell and a less honest one. The residual motion is real, measured, and so far unexplained, and any honest account of our galaxy's motion through the universe has to include it, unresolved edges and all, rather than quietly trimming them away for the sake of a tidier narrative. Whatever the eventual resolution turns out to be, the process of getting there will look like everything else described throughout this whole exploration. Patient, incremental, built on repeated measurement rather than any single decisive experiment, advancing not through sudden breakthroughs, but through the slow accumulation of slightly better data, slightly tighter error bars, slightly more confident conclusions year after year, until the current uncertainty either resolves into a mundane explanation or hardens into something genuinely stranger than anything covered so far. Every destination named so far in this exploration has turned out, on closer inspection, to be someone else's waypoint. The Earth spins, carried by its orbit around the Sun. The Sun orbits, carried by its slow circuit around the Galaxy. The Galaxy drifts, carried toward the Great Attractor. The Great Attractor itself drifts, carried toward the Shapley supercluster, sitting further out still. And somewhere beyond even that, an unexplained residual motion hints that the chain may not stop there either, that something else, mapped or unmapped, known or permanently unknowable, may be pulling on the Shapley supercluster the same way it pulls on everything nested inside it. There's no reason, based on everything covered so far, to assume this chain simply terminates wherever current instruments happen to lose the trail. Every single time researchers have followed one attractor far enough to identify what was pulling on it, they found another attractor waiting behind that one, larger, more distant, patient in exactly the way that makes the nearer pull look modest by comparison. Nothing about the pattern so far suggests any reason for it to stop. If anything, the pattern gives more reason to expect it continues than to expect it resolves. Whatever we are being carried toward, then, may itself simply be passing through, headed somewhere else, on a current with no reachable shore anyone has ever located, nested inside a current larger than itself, which may in turn be nested inside something larger still. This isn't a comfortable thought to end on, and I don't think it's supposed to be comfortable. It's simply the most honest place the evidence currently allows anyone to stand. I keep returning to the very first fact stated at the beginning of all this, the one about sitting in a chair feeling completely still, being wrong about it in ways too large and too smooth to ever register as motion at all. Everything covered since then, the spin, the orbit, the galactic circuit, the dipole in the ancient light, the hidden attractor, the mapped basin, the larger pull behind it, the unexplained residual drift, has all been, in one sense, an extended answer to that single opening observation. You were never still. You were never going to be still. Stillness, as a genuine physical state rather than a passing illusion of the senses, may not actually exist anywhere in the entire universe, at any scale, for anything. It's worth returning, too, to the specific numbers that open this whole exploration, if only to notice how much larger they've become by the time the story reaches this point. A spin measured in the low thousands of kilometers an hour. An orbit around the Sun measured in the low 100,000s. An orbit around the galaxy's center measured in the hundreds of kilometers a second. And finally, layered on top of every one of those, a bulk motion carrying the entire galaxy, roughly 600 kilometers a second, itself potentially incomplete, potentially missing a further contribution from something not yet identified. Each layer dwarfs the one before it, and yet each layer was, at the time it was first proposed, met with the same kind of quiet disbelief, the same instinct to assume some mistake had been made, before repeated confirmation eventually settled the matter. There's a kind of consistency running through every one of these discoveries worth naming plainly before this closes. Each one was resisted initially, not out of any particular failure of imagination on the part of the scientist involved, but simply because each new layer asked people to accept a larger, stranger, less intuitive picture than the one they already held comfortably. The Earth's spin took centuries to accept fully. The Sun's galactic orbit took decades of careful measurement before it became uncontroversial. The Great Attractor sat as an unconfirmed anomaly for years before infrared and radio instruments finally caught up to what the velocity data had already been suggesting. The pattern across every single one of these discoveries has been the same. An anomaly appears, resistance follows, and eventually, given enough independent confirmation, the anomaly becomes simply another accepted layer in an increasingly large picture of motion nested inside motion. There's no obvious reason to expect the currently unresolved residual, the dark flow question sitting at the edge of current knowledge, to behave any differently than every layer that came before it. That's worth sitting with plainly, because it reframes something that might otherwise sound purely abstract into something considerably more immediate. This isn't a fact about distant galaxies that happens not to involve you personally. It's a fact about the chair you might be sitting in right now, about the ground currently holding you up, about the specific patch of sky currently overhead, all of it caught, this very moment, in a drift whose full explanation still isn't completely settled, moving at a combined speed that would sound, if applied to literally anything else, impossible. I think what makes this particular kind of not knowing different from most other unresolved scientific questions is how personally it applies, despite how impersonally it's usually discussed. Most open questions in astronomy concern things genuinely far away, genuinely separate from ordinary daily experience, easy to file under interesting but distant. This one doesn't quite work that way. The unexplained motion isn't happening to some other galaxy, studied from a comfortable, uninvolved distance. It's happening to this one, the one you're currently a part of, the one carrying you along with it whether or not you've ever given it a moment's thought. There's a particular kind of vertigo available here if you let yourself feel it rather than simply nodding along at the numbers. Somewhere out past everything currently mapped, at a distance and in a direction nobody has fully confirmed, something massive enough to bend the path of an entire supercluster may be sitting, patient, unseen, exerting its pull the same way the Great Attractor once did before anyone had found a way to look behind the dust hiding it. Or, alternatively, there may be nothing so dramatic out there at all, simply a scattering of ordinary, mappable structures that better surveys will eventually locate, closing the gap through nothing stranger than more careful bookkeeping. Both possibilities remain genuinely live. Neither has been ruled out. The honest position, right now, is uncertainty, held without either forcing a premature resolution or treating the uncertainty itself as some kind of failure. I don't think there's a tidy way to close a story like this one, and I don't think forcing a tidy close would actually serve the material honestly. Every layer uncovered here revealed another layer sitting beneath it, patient, waiting to be found, and there's no principled reason to assume the layer currently being investigated is actually the final one, any more than the spin of the Earth turned out to be the final layer, or the Sun's orbit, or the pull of the Great Attractor, each of them seeming, briefly, like a complete explanation before something larger showed up behind it. There's a particular comfort available, oddly enough, in accepting that the chain might genuinely not have a final link. at least not one within reach of anything currently mappable. It removes a certain kind of pressure, the pressure to eventually arrive at a single, tidy, ultimate cause sitting behind everything else. Some structures in nature really do resolve that way, a chain of causes terminating cleanly in some foundational explanation. This one, so far, hasn't shown any sign of doing that, and there's no requirement that it eventually must. A current can simply keep going, nested inside larger currents indefinitely, without that openness being any kind of failure of explanation. It may simply be an accurate description of how gravity actually organizes matter across genuinely enormous scales, currents inside currents, all the way out, further than anyone has yet managed to look. I think about how strange it would have sounded to anyone standing outside on an ordinary night a few centuries ago, utterly convinced of their own stillness, to be told that the ground beneath them was spinning, that the sun above them was itself circling something invisible and enormous, that the whole arrangement was itself adrift, caught in a current reaching out towards structures so massive they'd eventually require their own separate names. Structures pulling on structures, with no confirmed end yet found to the chain. Nothing about that description would have matched anything they could feel, anything they could measure, anything available to them at the time. And yet every single piece of it was already true, the whole time, indifferent to whether anyone standing there that night ever found out. What can be said, honestly, at the end of all this is considerably more modest than a full resolution, and I think it's worth ending there rather than reaching for something grander than the evidence supports. You are moving right now at a speed and in a direction shaped by forces operating on scales your senses were never built to register. Some of those forces mapped and confirmed, some of them still genuinely uncertain, part of a current that may itself be nested inside a larger current, headed toward a destination that may not be a destination at all, but simply another waypoint, on the way to somewhere else entirely. Nobody standing anywhere inside this current has ever felt it directly. Not because the current isn't real, because it's exactly the kind of motion a body was never built to notice, smooth, steady, unbroken by any sudden change that might have registered as anything at all. The stillness you feel right now, sitting wherever you happen to be sitting reading this, was never actually stillness. It was simply motion too large, too smooth, and too old to feel like anything other than rest. There's a particular kind of quiet available in accepting that, one that doesn't require resolving the remaining uncertainty first. You don't need to know whether the missing piece of the ledger turns out to be an ordinary supercluster, waiting to be mapped, or something reaching from beyond the edge of the observable universe. Either way, the current keeps moving, carrying you along with it, the same way it's been carrying everything since long before you existed to wonder about it, and the same way it will keep carrying whatever comes after you, long after the question has either been answered or simply stopped being asked by anyone still around to ask it. And somewhere out past the edge of everything currently mapped, whatever is actually doing the pulling, whether it turns out to be an ordinary structure waiting patiently to be found, or something considerably stranger, reaching in from beyond the edge of what any instrument will ever manage to see directly, continues doing exactly what it's been doing this entire time, indifferent to whether anyone down here has finished working out its name. If any part of this has stayed with you the way it's meant to, the only thing worth doing with it is passing it along, the way the fact itself got passed along here, quietly, without much fanfare, the kind of thing that's more interesting once someone else has heard it too. That's the entire ask, buried in the middle of everything else, easy to miss, and probably better left that way. There's something fitting, actually, in ending a piece about currents nobody can feel with a request this quiet, this easy to overlook, since the whole point of everything covered here has been that the most consequential motions are often the ones that never announce themselves. The Earth's spin never announced itself. The Sun's orbit never announced itself. The pull of the Great Attractor sat unannounced behind a curtain of dust for the better part of a century before anyone found a way to look past it. If this particular current, the one carrying an idea from one person to the next, moves the same way everything else in this exploration has moved, quietly, without insisting on being noticed, that seems like the right way for it to travel. The current doesn't pause to explain itself before continuing. It never has. It simply keeps moving, carrying everything inside it, toward a shore that may not exist, or may exist somewhere so far out that no one currently alive will ever know its name. Patient in the specific way only something this large, this old, and this thoroughly indifferent to being noticed can afford to be.